and currently is working there as an associate professor. He has served different positions earlier, and in particular, he was at the University of Camerino in Italy in the quantum optics and quantum information group. His research interests range from Bose-Einstein condensate quantum optics to quantum simulations. So without taking more time, I would like to invite Dr. Roy to deliver his talk. Dr. Roy, please.
Yeah. Thank you, Dr. Mehta. Is my screen visible?
Yes.
Yeah. And my sound is also okay? Like
yeah, pretty much good.
Yeah. So
could you please make your slides full screen?
Yeah, I'll do that.
Yeah. Okay, sounds fine.
Yeah, okay.
Perfect. Yeah.
So, yeah, so thanks, and I must thank the organizer as well for Professor Panigrahi for inviting me to present my work this year's QIQT. And today I'll be talking about, in a topic which is not, much discussed in this event so far. So it's ultra-cold quantum matter and applications to quantum simulations and quantum information. So that's why, I'll start with the basics of ultra-cold quantum matter, why we have to consider this system for advanced applications, and then how we can do this, because external confinement will play a very vital role, which is called the trap. And then I'll be talking about quantum simulation aspects of it, like the presence of optical lattices and how we can control this system. Then localizations, so what kind of localized excitations can be observed in these systems, because the technology will rely on localized information, observation of it. So these are the things that, the kinds of localized excitations which are observed, and aspects of quantum informations, which can be derived from this kind of studies, and application to quantum precision measurements. So because these topics are not widely discussed in this event, so I'll basically give you kind of an overview. I'll include only the physics of it, not much equations, only the plots and physical interpretations. But, it is a collection of a number of aspects of it. So as I said, that I'll start with a very basic thing. This is an animation which says that the particles of gas at high temperature, it moves like classical particles, randomly it moves in space. But when you lower the temperature, things becomes a little bit different. The particles at de Broglie wave will be more pronounced, and they'll be, kind of start interacting each other. So they will start talking each other, and then below certain temperature, they lose their identity to have a single wave function. So this is the point where the system of particles will convert to a quantum domain. And this we say that the matter, when it is converted to a quantum domain below critical temperature, we call it as a quantum matter. So what are the, so special about this system? First of all, it is quantum. And second thing is that it's highly coherent. And, we have quantum systems. The coherence is a very important aspects of it. Unless it is behaving coherently, there are a lot of disadvantages of applying it to technologies. So this is important aspect. And it has to be highly tunable. So it is indeed highly tunable, because the formation mechanism of this system is relying on external potentials like, magnetic potentials, optical potentials, and so on. So it's highly tunable. It is having very long lifetime. Among all quantum systems, when you observe in laboratories, we have everybody struggles with the lifetime, and here in this system, the lifetime goes in the order of minutes, which is a very long lifetime to work with any quantum system. And this is laser control. This point is also very vital, because when you control the system, when you have the dynamics of the system, we can have magnetic fields, optical fields. But because of the sophistication of the source of lasers, we have lasers of different kind and different precision of frequencies. So the lasers controlled and these atoms in a quantum domain responds to the lasers. So that's one advantage always one takes, and it applies to the quantum technology. So all these properties makes it a very important candidate for quantum technology, for atom interferometry, precision measurements, and a lot of areas of quantum technology. But then the aspect is that localizations. So localization in classical physics, when you think about any information representing any information, that requires localization, because sine theta and cos theta cannot represent any information because it extends from minus infinity to plus infinity. And then if we superpose large number of sine and cos functions, just like Fourier series, we'll have some localized function, which in classical physics, which can be, when it is applied to optics, we call it as a pulse, which carries information, and a lot of other kinds of pulses and waves can be generated. Similarly, in this system, the localization is always, scientists look for localized entity, which localized entity has to be considered and how it can be generated in this system to have advanced application in technology. So because this is a matter and it's a very coherent, you can see the properties, and this resembles to a laser. So it's called the atom laser as well, to use it for different applications. Yeah. So to understand from the point of view of statistics, which is a fundamental, textbook in the physics, that this is a statistics of Bose-Einstein distribution. And so distribution function is having, chemical potential and the energy of the particle at temperature, absolute temperature, capital T. But if you go to high temperature limit, what happens that, chemical potential becomes negligible, because the particles behave almost like a free particle. And this part, exponential part, is highly dominating compared to 1. And then you are actually ending up with classical MB distribution function. But things are quite different when you go to a very low temperature limit, when chemical potential rises up to the minimum energy available to the system, which is E minimum, and then this quantity in the denominator, exponential term, will asymptotically will reach to 1, making this distribution function to blow up. And it means that the number of particles, which is proportional to the distribution function, will have a sudden rise when we have the chemical potential comparable to the energy. And that happens at very, very low temperature. So in layman language, we can say that at low temperature, significant proportion of atoms of gas in condensate in a state of lowest energy of the system. And this is actually the combinations of the two things, that one is the how matter is considered. So these are photon self-identity problems. Like if I say photon as the wave or particles, so it behaves differently in different situations. So it has a self-identity problem. Similarly, the atoms at ultra low temperature, below critical temperature and above, they have this identity problem. So although this is a matter, but then this behaves like a wave function. And this is a like kind of diagram where it says that at temperature, it behaves like a billiard balls, free particles. Then slowly you can see that de Broglie waves are kind of visible. Then it becomes, the de Broglie waves become bigger, and they start talking each other, finally to reach to a single wave function in the system. And this is, broadly defined as Bose-Einstein condensation. And they have predicted it, long back in 1934. But then it took, quite a long time to observe it in experiments. And in 1995, this is the only time when, they have observed it for sodium and rubidium, and obtained Nobel Prize in 2001, Cornell, Wyman, and Ketterle. So this is the animation, which is, simulation, which is done in Gila laboratory for rubidium atoms, rubidium 87. You can see this is a plot for momentum, the density, because it is composed of atoms. We'll be talking about the probability density. So it's a probability density in momentum space, two-dimensional momentum space with temperature. But when you lower the temperature, you see that the density suddenly rises. And that's the point where you cross the critical temperature and have the matter in a quantum form. So these are the salient points came out from this kind of observations. But then this one, which is that BEC occurred in momentum space, not in coordinate space, which suggests that in momentum you have to also control this system in real space. And in real space, when you have a localization in momentum space, it do not have a localization in position space. So it may have a problem to have it in technologies in laboratory. So you have to have some confinement in real space. So, and that only will allow you to have dynamics of this system in presence of external trap. So this is a little bit of, only the fundamental is worth mentioning this thing, because the origin of generating this quantum matter is completely different from any other systems. That's why the physics of it is very rich and having a lot of applications as well. So this is a second quantized Hamiltonian. You can see that this is a single particle Hamiltonian. And then if you integrate, you get for all the particles situated in different places. And then you have interactions between the particles. These interactions is dominant when you have very low temperature. And then finally, you are ending up with an equation, which is almost looking like a Schrodinger equation. But then you have one nonlinear term, which is given by blue circle in the order parameter or the wave function of the condensate. So this is the term which comes from this interaction. So when the atoms are interacting, they're very weakly interacting, but even if they're interacting weakly, you have this nonlinearity contributions to the equation. And this equation is famously known as Gross-Pitotsky equation. And the red circle, if you observe, and this is the external confinement which you require to control the BEC in space, real space. And how it is done is, you can see this picture, experimental, this is a magnet-optical trap to produce this BEC. So the center of the trap is here, and you can have laser in all 6 directions to trap and cool atoms. Also, you have, magnetic coils which are, counter rotating. But then after forming the BEC, it can be transferred to different chambers where you can apply optical fields and magnetic fields to have a different kind of confinement and use them for different applications. Yeah. So because we are talking about localized waves, the first category of wave which I'll be talking about is solitary wave. And I'll not go into the details of the explanations of solitons, but this appears in nonlinear system. And in the previous slide, I have shown that this is a nonlinear system, which is reflected by the nonlinearity in the wave functions in the Gross-Pitotsky equation. And so there is a possibility to have these systems, this existence of solitons when the nonlinearity, dispersion, dissipation, they balance each other. So nonlinearity actually breaks the wave, dissipation spreads the wave, and dispersion spreads the wave. And if you have a balance between this kind of effects along with the trap, then you can have a localized excitation, which normally does not decay within a laboratory frame. So that's the kind of thing. And then for that, you need an appropriate external trap. And in this work, the harmonic confinement is actually considered to show that how things can be controlled. And we have actually, generalized such system by making this is the same Gross-Pitotsky equation with a distributed coefficients. You can see this is the external trap, it's a nonlinearity, it's a loss and gain because imaginary coefficient is there. So all these terms are very general. So we can, all these analytical treatments are very tedious. You can actually have a trial solution and then go ahead with this. I'll just give you some instance that these are the consistency equations which you can obtain, and they have to be simultaneously solved. This the potential will be taken care of here, and then this x is the traveling coordinate with which the cloud will be moving. So let us give example that how solitons look like in harmonic and double well potential in some of our recent things. This is the, you can see the final expression of the solution for, a general solution. You can actually put a trap of various profiles to get such kind of thing, and then we have reported as a unified model in 2014. So because it can include various potentials as external trap. And recently we have reported about, because double well is a very important system for quantum information science. So if you put, if you load BCU inside a double well potential, then actually you can have a lot of quantum information science over here. You can see that things are tunneling from one well to another. You can have a collapse and revival. And then you can actually tune the kind of position of the depth to have different kind of non-local clouds in this system. So this was also reported in 2020. Now let us get into the aspects of quantum simulation. As I said that, the localized cloud, initially we started with soliton, but how we can use it for quantum simulation. So quantum simulation is not like computer simulation. It is the way of simulating the system to implement a different system which is non-trivial. For example, that let us give, so it's a better controllable system which can actually give you can mimic another system which is not much controllable. So here I give the this picture for a periodic potential, and in condensed matter these potentials are the solid state system. You generally see this potential, but in BC you create this potential by laser, and you create similar situation so that the physics can be correlated to each other, and that's the approach of quantum simulation. So observing and studying phenomena in one system can actually give some idea about the other system. So here, how optical lattices can be engineered. It's just a very simple example of it. You can carefully observe that there are two lattices. One is long wavelength lattice, one is short wavelength lattice. The blue solid line is short wavelength lattice. So this is a little bit, highly oscillating. And long wavelength lattice is the one which is given by a dotted line and pink shades. So now if you superpose both of them, things are periodic, but then you can have a position which is in between two lattice minima, which called as main lattice site. We have a minima over there, which is called the frustrated site. And this also is a very important in condensed matter physics, this kind of structure, because you have different lattice structures, hexagonal structure, triangular structures, and many other ratchet potentials, and many more, and which is actually a projection of it will reflect to this kind of potential family. Now, this is the first theoretical study where this quantum simulation and strong localization of Anderson kind is reported. So, experimentally, there are several works earlier, and people have been addressing this kind of studies, but then the background oscillatory lines are the potential, and the field plots are the density of the Bose-Einstein condensate. Now, from the plot 1, the potential is very shallow, and then that's why the cloud is not affected by the potential. But then as soon as you increase the depth of the lattice, periodic potentials, then the atom actually starts seeing the potential and then arrange them accordingly. So the maxima comes in a minima of the potential, right? But as you increase more, the depth more between the both the short wavelength lattice and long wavelength lattice, you will have a minima in between the main minima, right? This is we call as frustrated position. Now you see things are very different. Like they have come closer, but then there is also a small density which is appearing on the fluctuated side. That's a very interesting observations in any quantum system. And this strong localizations was obtained by analytical methods, but this actually directly reflects the experiments in Nature Physics 2008, where they have actually realized the Anderson localization in ultracold atom for the first time. Okay. So now, as I said, the Anderson localization, what is it? Because earlier I have discussed about soliton in this system, because this system being a nonlinear system is natural to observe soliton here. But what is Anderson localization? I'll be actually giving you a basic idea about it. So let us see that, the wave propagating in some random medium can lead to localization. So what is a random medium? You see that they are, these all oscillators in the first row. They are actually not random. They are identical oscillators, and then they have a wave, right? But then if you have random oscillators here in the second row, you can slowly see that somewhere the oscillations are more, somewhere it is not there. So it is a localization that some oscillations amplitude is localized in some space, and it is because you have a random superposition of oscillations. So this, basic idea can be reflected in many body systems where you have a large number of atoms. If you see that here, the extended wave function can reflect a periodic lattice. So this is the periodic lattice, each minimized for the atoms. So you have array of atoms or the potential which is found from lasers, which I said optical lattice. But if you form a two periodic structure, one is smaller, another is deeper. So if you overlap both of them, it will create geometrical frustrations, which I shown schematically in last slide. And then what is observed that the cloud which comes in the frustrated position, which I have shown in the previous work, is not a Gaussian, is not a Sekar-Pauli like soliton, but this is an exponential cloud, which is a very different kind of density profile observed in reality. And this kind of exponential cloud is called Anderson localization. Now the point is, although we have first experiments in 2008, and we have qualitatively shown it in 2014, there was no reliable study where one can prove that this is indeed Anderson localization in ultracold atom, which is normally seen in electron systems and other systems, but this also can be reflected, like simulated in many body systems under critical temperature. So here in a recent study, what we did is, so here actually the step one, I'm just giving you by stepwise so that things are clear to the students. And first you prepare a crystal of lasers, which is, these are two-dimensional crystals where atoms are added. Atoms are arranged over there. A solid crystal in condensed matter in left-hand side. Right-hand side, the same crystal is actually prepared by optical lattice systems. You can have optical lattices, lasers from all four sides to create two lattices, and then you can have such structure, potential structure. And this is actually shown in the middle. So it's using counter-propagating lasers from both the directions. Now, next what you do is you create a crystal disorder from lasers. So first you create the lattice, and then you have a long wavelength and short wavelength, and then you also have, you can see the potential here, which you say bichromatic because you superpose two optical lattices. One optical lattice will have some particular wavelength, another optical lattice will have another wavelength. So if you superpose both of them, is a bichromatic. So having two colors in other words. So that's why this name bichromatic optical lattice. Okay. So fine. So now next, what is it? That this figure is again, I have taken it from the first slide from Anderson localization. But here you can see in our model, A periodic lattice will have no localization like this. But as soon as you increase the lattice, and then there are models, we have modeled it in such a way that the depth varies like, particular parameter of the laser. And then you have a very localized cloud, very localized cloud. You can compare these two clouds, the first one and the second one. There's a drastic difference in the width of the cloud. And this happens due to the geometrical frustration on the potential. And that is not enough, because yes, we can see that the localization in geometrical frustrated minima is normally Anderson localization as per the experiment and also the analytical model. But then to prove it, we have modeled it, and then we have indeed seen that the participation ratio and changing with the laser parameter, that shows, there's a normal localization with increasing beta. Beta is the depth of the lattice, you can say. And then there is also another, another cycle of reduction in the participation ratio. And this part is the part for Anderson localization. So in this part of beta, so above say 4.2 or so, 4.16 around, if you measure the cloud, if you see the profile of the cloud, they match with the exponential profile, which we have actually modeled, and we have identified the characteristic length of the cloud as well. So this is a simple animation to see how the localization happens. Earlier it was in different lattice minima, but as soon as you increase the depth, you can see the localization suddenly comes. This cloud having exponential profile, and indeed Anderson kind of localization. So here, not only we go with this model of proving Anderson localization, there's a beautiful, flow of Anderson localized cloud, because as I said, that this system is already very coherent, and you have to just, kind of prepare appropriate localized object to study for your any quantum information applications. So here it is the moving of the Anderson cloud at different time. So it splits, and then it goes to the one side, then it goes to the other side. It becomes a single cloud. You can see the contour plot from 0 to, and then a single, then again this thing. So this is reviving, the middle part is reviving. So it's a kind of revivals, and also the distillation of atoms. Remember, this is not a field state. This is the probability density of ultracold atoms. So it's a matter wave, quantum wave, which shows this kind of revival structure in the form of Anderson localization. So this was actually reported recently in Physical Review. Now the point is, we discussed, solitone and Anderson localized cloud, both these categories so far, and this actually can be controlled using different lattice profile. And because it is not very easy to kind of predict this system, because this system origin is very different. In quantum optical system, the localized object is a coherent state, and one sees that a derivative of coherent states, say squeeze state, protonated coherent states, superposition of non-local superposition of coherence, which is called Schrodinger-Cat states. These are all very well studied object, and things are easily doable in experiments in optical setups. And but this system actually the formation mechanism is very non-trivial. So if you change the external trap, then one has to actually see that what is supposed to happen if the model is solvable then. So one has to actually have uncertainty that whether it is solvable or not. So we are fortunate to have a model for 4 optical lattices, connections of 4 optical lattices. This figure gives you a different optical lattices, 2, 3, and 4. And all these things separately gives you different non-trivial problems. And we have reported for 4 lattices, and you can see that how things are. This is a area of double wells. You can see that super lattices. These are super lattices of frosted double well lattice. You normally see that optical lattices, then talked about a bichromatic lattice, but here this is a double well lattice, which you call a double well super lattice, but that too also is having a geometrical frustrations. And this kind of structure is very important because normally we always look for non-local clouds, and we can tune tune the cloud by using such kind of potential for having non-local localized clouds for quantum information, just like COM states, Schrodinger cat state, and so on. So this we exactly reported using our exact method in last year. So this is we have to always kind of check about the stability of the well, and things are quite stable, and one has to know that up to which noise limit we can work with, so that the experimental setups can be prepared accordingly, and also up to what time we can observe. So these are the things, and this for triple potentials, triple optical lattice. This is an odd combination of optical lattice, is gives you very kind of different structure of the potential. Not even structures, asymmetric structures, and so on. And this was for triple lattice. Now, when you talk about soliton and we are talking about temperature, so we started with positive temperature, high temperature, and low temperature. But then when we talk about any temperature, we always assume that this is a positive absolute temperature scale, right? And but in standard statistical mechanics suggests that you should have also a negative absolute temperature scale, right? So but the problem is that in reality observing such system is very non-trivial, as that is why so far it was not observed, although the theory was more or less known to people. But then in 2013, it was first observed for ultracold atom. And we address here the first theoretical model for the soliton in negative absolute temperature domain. So here you see what is the salient difference for physically understand what is positive and negative temperature. Positive temperature, you can see probability goes down with increase of temperature, right? But negative temperature will have an opposite trajectory. So in equilibrium, if you have a larger density at higher temperature in equilibrium, then you can call this situation as negative absolute temperature scale. And but having this situation, you should have a minima at higher temperature, and also you should have an upper bound of energy. So that was very rarely observed in physical systems, and this was because it is a very tunable system and optical lattices are used for tuning the cloud. So this was first observed in 2013 in an experiment reported in Science Journal. So this is a momentum space. You can see positive and negative temperature. Now, what is our contribution is that we can use the same model, whatever potential they have considered. We have done the same thing, and you see that this is a potential for which a negative temperature is observed. And we have also modified it to frustrated lattice, and then you see that the existence of stable cloud at potential with upper bound of energy, having upper bound of energy. And also atom distillation, you can see things are distillating, not being dispersed also. So this is a very stable cloud at negative absolute zero temperature. We have quantitatively, shown that these are actually negative with these parameters for this particular lattice. And this was reported in scientific reports in 2020 by us. And this was, kind of because there are a lot of infinite amount of studies for positive temperature domain, but not much studies in negative temperature domain. And so once it is observed in the system of ultracold atom, it is natural to think about that how you can use it, how you can tune it, and but this does not come as an intuitive understanding because we don't see such system in reality around our daily life. So we have to study each and every situation. And so we have taken up this project for trap engineering. So if we change the trap and how things are, so whatever parameters are there of the laser, if I change each parameter, how the negative temperature will vary in the system. So that is what was studied. So these are the potentials which are responsible for this for different trap, the potential functions at different points. And then you can have a donut chart for beta is the depth of the potential. So omega is the frequency of the harmonic confinement, and L is the period of the optical lattice. So it is a, as you have seen, that is a combination of optical lattice and also a harmonic trap in expulsive nature. So all these parameters can have a different partition ratios, like N naught is the number of atoms, probability of number of atoms in the ground state, and the blue field region is in the first excited state for a first neighboring minima, and the brown one is the second neighboring minima. So first lattice site and second lattice site. So you can see that the blue field, yellow field region, which is the central region, gives you the localization. So that is can be observed from this plot in a very precise manner, that which parameter you have to take up for experiment to have a localized structure in negative absolute temperature domain. Okay, and this is a more detailed analysis of quantitative analysis of the thing. And we measure the temperature by using thermodynamic definition, using entropy, by calculating entropy. And so this work gives you the engineering of the lattice and the quantitative estimate of temperature in negative domain. Now, after discussing, this soliton and Anderson localized cloud in different situations, different lattices, and then different temperature domain. So this is one wave, which is a very surprising wave we normally observed in sea, deep sea, which is called the rogue wave. And this is a freak wave, and it suddenly appears and disappears. So it becomes very, kind of traumatic experience to the sea traveler, because suddenly, these waves can have a very high altitude, high wave, and then it can be also devastating suddenly. But the formation mechanism is not known, because that is why they call it as a freak wave. Suddenly it appears from nowhere, and then it also disappears. It does not remain for very long. But because water is a nonlinear system, basically, so you can actually people have been studying it in ultracold atom being a nonlinear system, and when it is behaving like a fluid. So water is also fluid. Here it is also fluid. So when you consider this as a fluid, you can try to see the generation of rogue wave in the system. So this is a rogue wave in disordered lattice. So we found that rogue wave exists in disordered lattice. So it's basically a quantum simulation kind of environment, but a localized structure like rogue wave is observed. So, but these plots will not give you actually the physics of rogue wave, but you can see the structure, because in short time it is very difficult to explain this plot. So I'll go to a 2D plot where you'll understand that the first row, this is the variation of the bright soliton. So this is a soliton which is bright, and second row gives you a dark soliton which is a dark. So it's a depression on the density, is the elevation on the density, and then increasing the lattice site, you get this kind of profile. Okay, from A, B, C, D, A to D, you get this profile for increasing the depth of the lattice, both bright and dark. And very interestingly, it was predicted that, rogue wave is having a negative density. You see that here, this is the rogue wave row, third row. You have a minima. This is the background. So there's a minima below the background, and then you also have maxima. So one wave having both depression in the density and as well as elevation in the density. And people have thought about it, and then some models are there. People predict that this may be a combination of bright and dark waves. But here we actually exactly show that if you add up these two, and all these two plots, say A and C, B and F, C and G, D and H. If we add them up with their proper values in the y-axis, then you'll get exactly the third one, and which is actually observed from our method, exact analytical methods independently. So this is something we have to solve this thing for bright soliton. This is solve something for dark soliton, and this is solve something for rogue wave. But rogue wave independent study gives you and the confirmation that this is nothing but a superposition of these two known solitary waves, but which makes it as a very surprising and suddenly arising and decaying waves. So these we have proven in this work in 2022. Yeah, so the last part of my talk is quantum information and quantum sensing. Probably I'm left with 15 more or 10, 12 minutes I'll spend on that. So, so how a matter wave can be, although, some of the works I have mentioned that those situations, those models can be used for quantum information, but here I'll be more specific about it, than how things can be done. But then I'll be go a little away from quantum simulation now. Okay, so I'll be not using the optical lattice anymore right now. So a different kind of traps to control the system can be used. So one of them is a ring trap. So this is experimentally highly, popular trap people have been doing in labs, and a lot of applications are going on. Precision measurements applications are going on in this trap. And we invent a new phenomenon in this system called fractional errors, which is normally observed in optical fiber as a Talbot effect, and then also in atomic systems, molecular systems like fraction variables. But here in this system, we predict for the first time that, if you allow the cloud to evolve, then it splits into different parts, different mini clouds, which are the replica of the first one. So this is the phenomenon. And here you can see that this horizontal line gives you a time frame, time scales where they're supposed to be in which part or so. So this is the initial time, and this is the revival time. In between, they split into say 1/8, so it's a 4-part here. It's a 5-part here. It's a 2-part here, and so on. So you can this formula and the relation of along with the relation of fraction errors will tell you how the system dynamics should be here. Now for that, a trap preparation is very much important. With experimental parameters, we have exactly proposed that you have to tune the trap in such a way that each of the double well, this is the 2D projection of the ring, right? A ring, you can cut it in one plane, you'll get a 2D double well. So, one-dimensional double well. And this double well should be tuned, is formed by harmonic trap and a Gaussian trap. And both of them should be tuned in such a way, both the pulse and the trap field, outside field, can be tuned to have a harmonic modeling of the lower levels of the well, so that the cloud you use for simulation or in experiment should mimic the ground state wave function of that potential. And then this cloud will be like if you put a BEC, load a BEC over there, it will be a BEC cloud. So this looks like in this 3D plot, this one is the cloud which will be traveling along the ring, and we have to see that what will happen. Now I'll show this animation movie that you can see is the first animation. You have to observe that in certain times, time is changing, and you see a specific time with different number of clouds. And this is actually observed in many experiments with interference, but this kind of fraction variables were not predicted earlier. So these are snapshots which we have published in Physical Review that different time, exact which time one has to observe in experiments and how many numbers you get, along with the stability and the phase correlation with that. So this is the phenomenon which is very much useful for quantum information in other systems. So this is a direction we are giving that, one can use and observe such clouds and go ahead with the same applications which were observed in other system. Yeah, so this is also kind of reflected in autopopulation functions. And then we exactly mention that which parts. So these numbers are all parts, how many clouds should come. And this is the formula for fraction error. So yeah. And this is additional thing that, during the fractional errors. So if you switch off the trap, central Gaussian trap, what should happen? So now let us play this movie. It spreads, and then I switch off the cloud, switch off the trap, and then it goes at the center. And you would expect that when it goes to the center, because the clouds are equally distributed on the ring, so you will expect this kind of superposition structure. But then it is not, because you have a very interesting phase structure on the periphery of the ring, which makes your different spatial interference. Earlier, I was talking about non-local superpositions when the clouds are separated, placed in different positions. But now it is a spatial superpositions when the cloud actually come over each other to superpose and give you a interference structure. Yeah. So this gives you definitely scope for quantum sensing. Yeah. Now, strong and weak measurement. These are the two methods of precision measurements which are widely used. Strong measurement is for non-local clouds. Weak measurements are normally applied for two quantum wave functions when they are hardly separated. So you cannot distinguish them, but then you can have a meter shift. You can have amplifications in their weak value, which can be experimentally measured to have the weak value measurements. So we have addressed this for BEC in harmonic trap for both the measurements inside harmonic trap. When they're oscillating, we can have such situations. And the last example, which is the quantum sensing, the direct approach. And here also the trap is very simple. There are a lot of experiments on this trap. It's a harmonic trap, but then you can have some barrier, just like a path of the laser, you can put some beam splitter or maybe some other optical elements, which actually makes it a two-part. A beam splitter makes it a two-part. If it is a 50-50 balanced beam splitter, it splits into two equal parts of the input beam. So similar thing, because here we are talking about atom lasers. So we actually intuitively kind of understand that the same thing should happen if you create a potential barrier on the path of the atom laser. So here it is optical analog. You see, you have 2 mirrors, and then you have beam splitter here. Here, the horizontal plates are all beam splitter, then input beams are coming. And this is a 50-50 beam splitter, which you can control by adjusting the height of the beam, which behaves like a trap. So is a spikes of particular height, which can control the reflected and transmitted probability in equal 50-50 manner. So that we actually exactly do it, and then we go ahead with observing this. So this thing, if you look at this, then it is coming and striking on the barrier, the beam splitter. So it splits into 2 parts exactly. Then it comes back. Because it's a confined system, I put two beam splitters. Now you see very fine structures, interference structures come in between, and definitely people will be eager to get substructure for precision measurements. So we go ahead with plotting these things in phase space, because quantum interferences are nicely visualized through Wigner distribution function. So these are the interference structure which arises in phase space. This is the central part which is zoomed, and this is the work by Zurek, which says that this structure, these are very small area, is below Planck, definitely below Planck scale, and but these structures are not meaningless. They are meaningful. They play a very vital role for quantum precision measurements. And so he has mentioned about harmonic oscillator system and chaotic gas, but nobody has mentioned about ultracold atom. But here we address about ultracold atom. We exactly prove that this scaling law is satisfied for ultracold atom. And not only that, once we know that, okay, this scaling law is applicable, which we prove it with exact experimental parameters, and then we go ahead with, estimating parameters, say position, momentum, force measurements, how precise we can measure things, and also indirect measurement of temperature, because temperature measurement is direct measurement is very, very difficult. So people actually do it for indirect measurements. And here we have the precision of the temperature measurement up to picokelvin, which is the highest limit of temperature measurement reported so far. And this we reported in recently and physics literacy. So that is all. I think I'm more or less on time. And this is my PhD students with, these works are basically Borun, Abdul, Batin, Prodot, Vashu, and Raghav. These are the 4 students who are involved in this work. Vivek and Sonali, they are working in the algorithms in quantum machine learning for continuous variable quantum computation. And Vicky is working in nonlinear optics, and Joyce is in quantum optics in different systems, not in BEC. So these are the thing, and these are my other project students. I have to thank the collaborators because somewhere, I have discussed with them, some of the works are combined works. So in epilogue, we have discussed about different localized excitation, how they can be formed in nonlinear systems of ultracold atom. And this is being a quantum matter, very useful for quantum technology. So the entity which will be used for going ahead with advanced applications are discussed, and with experimental parameters and the setups. So yeah, so then I should thank all of you for listening to me for so long. Thank you. Yeah, I can take questions.
Yeah. So let's thank Dr. Roy for this exhaustive talk. If there are any questions, please raise your hand, or you can even type it in the chat box.
I have a doubt.
Yeah, please, Lava, go ahead.
So, can we trap any kind of atoms in these optical lattices, or is there any specific properties?
Yeah, so this trapping actually depends on neutral atoms. Okay, so the neutral atoms are trapped by optical lattices, not any atom, because if you have a charged particle or have some other kind of particle, then it will have a different kind of force acting on it, then you may not be able to trap it. So it will interact in a different way. So,
okay. So, any neutral atom we can trap?
Neutral atoms, yes. Okay. Alkali metal neutral atoms can be trapped, yes.
Okay. So the potential is created due to the lasers that we are using.
Right.
So that electromagnetic, electric potential, is it so?
Yeah, so it is a, you can think of like, the potential can be created in a different manner. Say, for example, magnetic field. But the problem with the magnetic field is you have a less tunability, because magnetic field potential is created by coils, different engineering, different coils of different shape, different engineering, different width and turns and so on. So, in one setup cannot give you varieties of potential. So that's the problem. So laser can, kind of play a vital role on that. So as I said in the beginning, that magneto-optical trap can have the BEC, and then you can switch off the other trapping potential, and then another set of potential which will act like a external potential to the Bose-Einstein condensate. One trap will be for generating it, and then there will be another potential which will act like external trap to kind of having the applications. And in a recent experiments, people have been doing it. They're transferring the atoms to cloud in a different chamber, a fresh chamber, and then they are applying external lasers of different kind, as I mentioned, the superposition of lasers of different intensities and so on. Definitely lasers are synchronized, like there has to be a very synchronized frequencies and number. So yeah, so that's something.
I see another hand raised, Ranjit Singh. Please go ahead.
Yes, thank you for your talk.
Yeah.
So when one studies nonlinear Schrödinger equation of one dimension, let us say x, then the solution is conservative. That is, soliton profile does not spread over time. But in case of 2D, soliton becomes unstable. That is, soliton profile spreads over time. So my question is, do you have plans to consider 2D case and see whether wave function is spreading or not?
Yeah, so if you have seen some of my applications where in ring trap, which is a 2D trap, okay. And definitely we have to take care of the stability. The stability which is considered in literature is without trap. So if you do not have external trap, then there's a serious questions of stability for the number of atoms which is greater than some critical number for attractive interactions. Okay, but then if you use external trap and which can actually stop making the cloud unstable, so that is why you have to check in a given trap. It is not enough that you just model a trap and use it, and then at the end of the day you don't have a stable cloud. Definitely you have to keep checking that, but then physically the trap will actually prohibit the instability in the cloud. So I'd say that. So 2D BEC, yes, definitely you can do. 3D BEC also you can do, but then you have to be within the limit of number of atoms for a given external trap.
Okay, so second question is on slide 36. Ring 1 is coupled with ring 2. So my question is total energy is conserved in two rings? You are changing the coupling coefficient by changing the distance, I think, between them.
Which
right?
number of slide you mean?
36.
36. This is the one, right?
Yes. So you are changing the coupling parameter by managing or changing the distance between them, right?
Yeah. So this is just my drawing. I'll go to the actual diagram of it. Okay. Yeah. So this is the actual diagram of it. Now, what is your question?
The question is the total energy is conserved or not?
Yeah, yeah. So that's a good question, actually. Basically that we are always talking about number of atoms. Say, I start with a cloud, which I have given in the beginning of this work. This is the one. Say this is the cloud I'm talking about at t equals to 0. And say this is having a number of atoms 10 to the power 5. Now, when you have, split it into 8 parts, so the number of atoms will be divided. So it is definitely normalized to a function having a total number of atoms, which is conserved. Yeah. So it's conservation is taken care of.
Thank you. Last question. Could you please name of the software packages you used or using to simulate problems considered by you in your presentation?
Yeah. So as I said in the beginning, that all these works have two aspects. 60% works are all analytical works. Like I start from the equation and solve each of them. These plots are not this one, but earlier all plots were of analytical results for quantum simulation part. But this part is numerical, also analytical, both combined. The numerical part of it is done by split step method. Split step Fourier method. Okay.
Okay. Thank you. What is? Could you repeat once more name of the software package?
Yeah, split step, split.
Okay.
It, so the Hamiltonian is splitted, so it's a split step Fourier method. It is a very well established method for solving nonlinear differential equation. Yeah.
Thank you.
So I guess if there are no more questions, we can once again thank the speaker and close the session maybe.
Yeah, thank you very much.
Yeah, thank you.
Thank you. Bye.
Yeah, bye-bye. Thanks.